So like I said, before break, we started some work before break, but yeah, it was a long time ago. So I'm going to start from the beginning. And if you guys could just follow along for the first couple of things. Actually, this looks like we did one thing in this class. So again, this is page 8.5, meaning it's the page in between page 8 and page 9. I realized when I started with my third period class one day, I'm like, it's like I forgot some notes. So I must have forgot a whole page of notes. And so that's why we had to add this sheet in. So it goes back to absolute time, which was the very, very, very first thing we did in this chapter. If you remember, we did absolute versus relative time at the beginning. Now, relative time, do you guys remember what relative time was? Clearly my reference or my notes are blank here. But what did relative time do? Yeah, this just puts events, and you guys already have this, or dates in order, meaning I'm older than you, or I was born before you. What does absolute time do? And as we had in our notes, absolute time gives an absolute time or a date of an event. And I gave the most famous date you need to know for this year, April 5th, 1983. So that's my birthday. That's an absolute time, April 5th, 1983. But like I've said many times already so far this chapter, it doesn't have to be down to the date, the exact date or the exact time. It just needs to be a specific time period. So I could also say I was born in April 83 or April 1983. You guys know what that means. Okay, you can find that in a calendar if you needed to. I could also say I was born in 1983, which again, doesn't give you the date or the time. You don't know if I'm already 39 or if I'm going to be 39, but you can tell I was born in 83. So you could point to that on a calendar. Same with if I said I was born in the 80s. Still a huge time frame, but it narrows it down. And this is similar to how on our reference table, I can give you an exact millions of years, or I could give you a period, or I could give you an era or an eon. Those are all absolute times. To find, to determine absolute time or absolute age, we will use what's called radioactive dating. So it looks like clearly we might have wrote the vocab word, but never wrote a definition. So radioactive dating is used to determine absolute age or time or date, whatever absolute we're talking about. So if you obviously didn't have radioactive dating. You had the word, but not the definition. Now, radioactive, and I believe we started here and I kind of ran out of time, but if not, let's start here now. When you hear radioactive, most people are thinking nuclear stuff. So nuclear bombs are radioactive. Nuclear power plants are radioactive. Chemotherapy has radioactive elements. And that's actually right where we need to start. We're going to start with a radioactive isotope. So this is a chemistry vocab word. So we're in earth science. So this is a little bit above your head. What we need to know about a radioactive isotope is it's an unstable element. There's more to it when you take chemistry, but for us, knowing it's an unstable element is good. Now, describe what I mean by unstable element. So first of all, do you guys remember what elements are? Yeah, that's literally all I was going to say. Do you remember this thing from like 6th, 7th, or 8th grade? Periodic table of elements. There's a lot going on here, and you learned a lot about it. You might not remember, but the basics is all of these guys up here are elements. You know that. Oxygen's an element. Carbon's an element. There's more. You might not remember anymore. Oh, hydrogen, you know that one. You probably remember hydrogen. Those are all elements. Some of them are stable, some are unstable. What does stable or unstable mean to you? What's unstable mean? Okay, not balanced, I think is probably, so which is something that's not strong is probably not balanced. So if you were to walk on an unstable like bridge or an unstable ramp, it's wobbly. What if I said one of you guys were unstable? If there's an unstable student in my room. I couldn't hear you. What? I still can't hear you. Yeah, it doesn't really fit. Or could at any moment explode, and by explode, it could be anger, could be sadness, could be happiness. Like my daughter is sometimes unstable because she's like literally bouncing off the walls, insane. Not like literally, but you know what I mean. Unstable can mean a whole lot of things, but it just means it isn't sitting still comfortable. It has to change. So some of these elements are unstable, meaning they are not happy the way they are. They like to change. And what they change into is called the decay product. And a decay product is what the isotope turns into. So these unstable elements will decay. Decay. If I say decay to you, what does that mean? Break down, decompose, rot. If an apple was to decay, can you picture what an apple turns into? Brown, slimy, stinky, yucky mush. So with radioactive elements, it's the same idea. We have one original thing that's not stable, just like an apple's not stable. It doesn't stay an apple very long. It decays pretty easily. An unstable element, a radioactive element, is going to decay into something else, just like the apple decays into that brown, mushy disgustingness. And by the way, side note here, nothing can change how fast an element changes or decays. We'll go with decays. Nothing can change how fast an element decays. Now with an apple, are there things we can do with the apple to change how fast it decays? Yeah, what could we do? Okay, so you could eat it. What's another thing that, saying an apple's sitting here, what could I do to change how fast it rots? Change it to temperature. So if I keep it in a fridge, it'll decay slower. If I put it in direct sunlight in a hot room, it's going to decay faster. I could add chemicals to it. Have any of you ever put lemon juice on an apple? If you cut up an apple and put it in your lunch, you know how it turns brown really fast? If you put lemon juice on it, it'll actually slow how fast it turns brown. So it slows how fast it starts to rot. That's what they do with, the sliced apples like you get in the McDonald's Happy Meal. They basically have lemon juice on them, citric acid, which slows down how fast they decay. Does it hurt you? No, lemon juice is fine, but it does a chemical reaction to change it. But with radioactive elements, so those guys on the periodic table, there is nothing. You can't heat them up, you can't cool them down, you can't add things. They decay at the same rate no matter what. And that decay rate is called the half-life. Based on the word half-life, what do you think it means? How long half the life is. That's basically what it is. Officially, it is the amount of time amount of time it takes the amount of time it takes for half of a radioactive isotope spelled isotope. So the half-life is the amount of time it takes for half of the radioactive isotope to decay. And the last things we're going to do on this page, and this is why you need your reference table if you don't have that already. ESRT page 1, and the chart is called radioactive decay data. So once you write that, turn to page 1, and we're going to take a look at the radioactive decay data chart. So we're looking in the upper right-hand corner. So again, you got, I'm sorry, left. Don't know my right from my left. So if you don't have your reference table out, because I know you can't see mine, I guess maybe unless you're in the front row here, grab your own reference table. We're going to look at the upper left-hand corner. This chart does not have much on it. It lists 4 different radioactive elements. There are more radioactive elements, but these are the 4 that you are going to be responsible for this year. So they list the unstable element. Then it talks about disintegration. What do you think that means, disintegration? How it breaks down. So we have something, arrow, something. So what do you think? The C14 turns into, what do you think? Nitrogen. Do you have to memorize these? No. For the record, they're listed in a couple different places. So there's nitrogen right there. On the back, there's carbon. But if it does not list it, like this uranium, you will find it nowhere else. Same with, well, is PB on there? No, PB is on there for uranium. PB is lead. What's not on there is this one, argon, right there. If they don't have it there, you're not responsible for knowing it. But anyway, so what this means is carbon 14, the arrow means it turns into nitrogen 14. This next one, potassium 40. So potassium 40 can turn into either AR40 or CR40 or CA40. Again, you don't need to know those letters. Uranium turns into PB, which is lead, and uridium, which is RB, turns into SR, which is strontium. Again, you don't need to know those. All you need to know is that whatever comes first is what it is originally, and then what it turns into. The last column is half-life, which means, again, how long it takes for half of the radioactive element to decay. So let's talk about carbon 14. So carbon 14, what's it turn into? So it goes to N14, which means carbon 14 turns into nitrogen 14. That's what the arrow means. And it says it has a half-life of 5.7 times 10 to the third. Okay, we got to talk about scientific notation. Do you guys remember scientific notation from math class? Times 10 to the third. What does that mean to do? How many places? 5.7 times 10 to the third is 1, 2, 3 places. Fill in the zeros. That's 1, 2, 3, comma. It takes 5,700 years for half of the carbon-14 to change. That's what that means. And so what I'm going to do is I am going to hand out a radioactive element, a pretend radioactive element to every single one. I don't have any rubber gloves. I'm going to put my hand in this Ziploc bag so that I don't touch anything. And the radioactive element I am about to hand out to you is a Twizzler. Now, due to COVID protocols, if anybody would like to come put on hand sanitizer before they touch the Twizzler, you are welcome to. And then I would like to remind you that you are not allowed to eat in my classroom and you have to save this for your lunch. Okay? So I'm going to hand you out a Twizzler. If you choose never to, you can actually take one. If you choose never to eat your Twizzler, that is up to you. But again, remember, COVID protocols mean you have to eat your Twizzler in the lunchroom. I am handing out two because who doesn't love a good Twizzler to save for your lunch? So again, I said these are radioactive Twizzlers. What does that mean? What happens to these Twizzlers? What does that mean that they're radioactive? Based on the definitions we've been talking about here in class, guys. Somebody come on, work with me here. Radioactive elements, what do we know about them? They break down, they change. They're unstable elements. So these Twizzlers are unstable and they're going to break down. By the way, what do Twizzlers break down or change into? Huh? Nothing. When you eat them, don't overthink this, guys. When you eat a Twizzler, what does it change into? Poop! 100%. These Twizzlers will decay into poop. I will tell you a little side story. I do this activity every year. And the first year I did it, or one of the first years, I should preface this by saying, my husband works nights a lot, so I'm home alone at night. And I heard a crash in the house, like a thump. And I thought to myself, well, that sounded scary. Maybe I should go check on it. Why? Because who knows what's going to cause a thump in the house in the middle of the night. Well, what if it was somebody breaking in? I should probably check on it. But then I thought to myself, nah, if it was somebody breaking in or something bad, the dog would have barked. Well, it turned out the dog wasn't barking because it was a bag of Twizzlers falling off the shelf and onto the floor, and the dog was devouring them. The dog ate one of these huge family-sized bags of Twizzlers. Now, the dog is only a 20-pound dog, and she ate this whole bag. I will tell you that Twizzlers, when you eat the whole pound of Twizzlers, they don't actually change into poop. I know for sure because the backyard looked like it was littered with broken up pieces of Twizzlers for like the next 2 weeks. Like they literally just passed through her body, similarly to corn, but it was Twizzlers. Anyway, that was enough of that story. Does everybody want? See, now you don't want to eat your Twizzlers, do you? But so does my other dog. You guys have something in common. No, said my other dog likes dog food. Anyway, really off topic now. So these Twizzlers are radioactive Twizzlers. Remember, radioactive things are unstable. They don't stay the way they are, they change. These Twizzlers also change. They will change into poop. We are going to walk through how half-life works with the Twizzler. So let me ask you this. Here's a Twizzler. I'm going to tell you it has a half-life of 1 minute. What does that mean is going to happen to this Twizzler in 1 minute? How much of it is going to break down in a minute? Half of it. By the way, what's going to happen to the other half? No. What did we just say happens to Twizzlers? What do they change into? Connor, say it. They change into poop. So half your Twizzler is going to break down into poop in 1 minute. So we're going to actually graph this. So if you would turn the page to page 11, which you'll see is just graph paper. So on our x-axis, we need to write time. And on our y-axis is going to be percent. So we have time and percent. So we're going to start off by graphing the Twizzler originally before any time has passed. Basically what I'm asking you to do is put your Twizzler on your graph paper and we're going to basically trace it. Doesn't have to be perfect. And you're going to make yourself a bar graph. And if you could kind of quickly shade that in, it doesn't have to be perfect, but just so you can see it a little bit better than just tracing it. This, and wherever the top of that is, you're going to label that 100, because that's 100% Twizzler, right? You haven't eaten any of it, so there's 100% of it left. And this does not have to be perfect, just basically trace your Twizzler. Now I told you that after a minute that's how long the half-life is. So when I drew this bar, how many minutes had passed? None. No minutes have passed here. So now it's been a minute. It's probably been more than a minute. Let's make half of your Twizzler disappear. So you go ahead and rip your Twizzler in half and save, put aside the other one and save that for your lunch period. And now how much of your Twizzler is left? Should be half. And that's what we're going to do. We're going to go ahead and we're going to trace the remaining part of the Twizzler. And what percent is half, by the way? 50. So you're going to come over here and label that 50. So we now have 50% of the Twizzler. Now, how much time, if we had done this exactly, how much time should have passed? 1 minute. Oh, it actually was legit a minute since I told you to, because it happened right on the 12th. So a minute has passed. So what should have happened to this Twizzler now? The half of a Twizzler. How much of this half in a minute should have disappeared? Half of that. So half of the half has now changed. And we're going to trace that. And again, how many minutes should have passed now to get to this part? 2 full minutes have passed. And what percentage is left? What's half of 50? 25. Now, again, this is not something you have to know off the top of your head. To figure out, you just take, it is easy, at least so far it is. So we took the 100, we divided it by 2, cut it in half. Take the 50, divide it by 2. Oh, it's exactly a minute again. So by the way, 25 divided by 2, 12.5. So take your remaining Twizzler, that 25% you had left, break that in half. It is getting pretty small. Trace that. And I just did the math, remember, that was 12.5. And how many minutes have passed? 3 full minutes have passed. Can you do it again? Oh, we're not there. We still have 10 seconds left. Okay, and 5, 4, 3, 2, okay, 1. Now make half of that decay. So take your 12.5 and cut that in half. Half of 12.5, so take 12.5, divide it by 2, you get 6.25. Could you do it again? You can, but it's gonna get pretty hard to do. In fact, I'm not sure, yep, I was able to get one last one, I think. So I did this a little early, but I think you guys get the point. And that would be 3.125. Again, just doing the math by dividing by 2. Now, technically, could I do it again? Okay, might need to get out like a sharp knife. Then would I technically be able to do it again? Yep. Technically, would I be able to do it again? What do you guys know when you keep cutting things in half? It gets smaller, but is it ever going to disappear? If you keep cutting it in half, technically. No. By technically, I mean like if mathematically, it will never ever get to 0. If you just keep cutting in half, it's going to get tiny. It's going to get so small we can't use it. And after a while, you can't even find it, but technically it's still there. And so that's what happens in real life. Sometimes it gets so small that they don't even bother looking for it. All right, so this is a graph of a Twizzler with a half-life of 1 minute. How would this be? How would it look different if I said this Twizzler has a half-life of an hour? So, okay, so first of all, we wouldn't have it wouldn't have time to do it. But let's say I did have time. I did this all day. What would my graph look like? Legit the exact same. Okay, it would start up at 100. An hour would go by. You'd be down to the half. Another hour would go by. You'd be done with the quarter. Another hour would go by. You'd be down to the 12.25. Another hour would go by. You'd be down to the 6.25. And then finally another hour would go by and you'd be down to the 3.125%. Next question. How would this graph look if the half-life was 5,700 years? If I had time, it would be the exact same thing. Well, okay, good point. Nobody's got that kind of time. But my point is, it doesn't matter what element it is. It decays in the same fashion. It always goes from a whole to a half to a quarter to an eighth to a 16th, or from 100 to 50 to 25 to 12.25. Doesn't matter. The only thing that changes is how long that takes. So how this works is if they find something that's 50% poop and 50% Twizzler, where would that be on the graph? 50% Twizzler, 50% poop. The 1 half-life. So they don't know, so then they have to know the half-life of if it was Twizzler, we'd know it was a minute old. But if it was carbon-14, we would know if it was half carbon, half nitrogen-14, we would know it's 1 half-life old, so 5,700 years old. So they just compare the ratios to figure out how old it is. So technically 2 last things we need to do. This is what a bar graph would look like. I want to change our bar graph. I want to make it into a line graph. To do this, let's put a dot in the upper left-hand corner of each of our bars. So it's 100. I'm putting it right on the y-axis. Then for this one, so on the upper left-hand corner of each of your bars, put a dot. And now we're going to carefully and smoothly connect these. As best you can. Now, this we know keeps going. So it's going to keep going down. Will it ever hit 0? No. So I want you to take your line and draw it out, but don't let it touch the 0. So this is the isotope line. The last thing I want to do is graph the poop line. So no, I'm not going to actually get out some poop and measure it, but work with me here. When we had 100% Twizzler, so this one right here, I did not eat any of it. When there's 100% Twizzler, how much poop is there? None. If you haven't taken a bite, you're not digesting it yet. So we need to draw the poop line. So that's going to start with a dot down at 0, 0. Now, when I've eaten half of the Twizzler, how much will it have changed into poop? Half. So that we already have the dot there. Now, how about this? When I only have this 25% Twizzler left, how much has changed into poop? Perfect. The rest of it. So if you don't know where you got that number, you take 100 and I have 25. Whoa, take 100 and I have 25% left, so I subtract them. So when I have 25% Twizzler, I have 75% poop, which is halfway here. So just estimate that at your halfway and put your dot at the 75. When this one's down at 25, that go directly above that to the 75. How about when I have 12.25% Twizzler? I subtract those and I get 87, which again is halfway between your 75 and your 100. And one last question. Will my poop line ever touch 100? No, why not? Because I'm never eating all the Twizzler. Good. So if I copy, now again, try your best to get that as a nice smooth curve that would never touch 100. And I'm going to label this one poop. Now, yes, it's poop in this example, but if it was carbon 14, it wouldn't be poop, it would be nitrogen 14. If it was uranium, it wouldn't be poop, it would be lead. But again, it doesn't matter what elements they are, they still work the same way. So like I said, guys, eat your Twizzlers in your lunch period and do your homework, which are the 4 questions on page 13. I am not asking you to do a lot, but please actually attempt these so we can see what you're getting and what you're not getting. Anybody have any questions about what needs to be done? Okay.